And I will present some work here today that is Sagi Haji Sharif, my colleague on the technical faculty, and I are doing. I can mention that this is a really interdisciplinary project. I'm a professor in gender studies, which doesn't necessarily mean that it would be obvious that I work with synthetic data, but Sagi and I have known each other for years, and we've been talking back and forth about her work with machine learning and my work with gender. And after a while, those conversations seem to actually be very, very well entwined. So this is what we've been doing recently. We have money from both WASP-HS and Vinova to work with these questions. And I will just give you some background first on why I'm interested in synthetic data and how Sagi's work comes into that. And then towards the end, I will be showing you some concrete examples of the results that we're having in our work. And I will open up for some questions at the end. I hope there'll be plenty of time for that. If you don't have a chance to ask a question, but have a question you want to ask me later, feel free to drop an email. Right, so professor of gender studies, what does, I don't know anything about AI, right? But I do know an awful lot about bias. And even though I'm actually over here at gender studies right now, I've been working for a long time in the field of science and technology studies, looking at the way that technology and especially diagnostic and treatment technologies for the medicalized body have been entwined with and entangled with understandings of what is a body and what is a healthy body and what is a subject in society. So I come to this work from, I guess you would call it the medical humanities now, but a really long career looking at how medical knowledge is produced, what that says about the body and what our body says about medical knowledge and that intersection. That said, because I've been looking at, among other things, gender and ethnicity around the medicalized body, I've been really interested in things like bias. So just to put it out there, I know that bias and especially fairness is something that gets spoken about a lot in the machine learning community and other types of computer science technologies fields. I will be talking about that in a second, but I want to mention that the stuff that we do over in gender studies is slightly different. So we think of bias, for example, as supporting or opposing a particular person in a way that doesn't necessarily jive with, say, a meritocracy decision about a person's ability to receive resources or a promotion or whatever. And this can be both explicit bias and it can be implicit or unconscious bias. And the reason I have an orchestra here is because one of the most famous examples about talking about implicit bias comes from the woman whose research, Claudia, who won the Nobel Prize last year in economics, her work that she did in the 90s looking at orchestras. Orchestras have long been dominated by male bodies or men, both as conductors, but also as the musicians. There has been for decades work trying to change that, but it went very, very slowly. And after a while, people started to do, say, blinded auditions. You get into an orchestra by playing for an audience, a jury in the audience. This is an audition. After a while, people said, why don't we have these blinded auditions where people play behind a curtain and see if that will make a difference, if maybe like there's some sort of bias going on in the juries and their jury selections. So they started doing that, and to a little extent, it changed, and there were a few more women being selected for orchestras. But then an experiment that was done in the 90s said, let's take this one step further. And they had orchestra auditions. They set up an experiment where they had orchestra auditions first played in front of a jury without a curtain. Then they pulled a curtain and everybody got to play the same piece again, individuals one by one. And they saw that actually there wasn't a huge amount of difference. There was still many more men being chosen in the curtained selection than as in the regular one, even though it was 50-50 who were like auditioning. But then they said, let's take it and we would do one more iteration, but this time we draw the curtains and every soloist has to come onto the stage in their stocking feet so that nobody in the audience could hear the dunk, dunk, dunk or the click, click, click of the feet coming in. And then suddenly it was 50-50 or basically 50-50. And this is one of the sort of like foundational examples of implicit or unconscious bias, that we make decisions based on many, many more things than just what we claim we're making these decisions on. And that trying to figure out how we're getting the input into these biases is a really important way of trying to think about how we can try to make our practices more just and equal. Okay. So that's what we think about with bias. That's not necessarily how we talk about bias and fairness in computer science, but both conversations are really relevant, especially for the fact that we're building lots and lots of systems right now that are going to be staying with us for a while. And here I'm going to talk about technical obduracy and the reason that it's important to think about technical obduracy. Give me 3 minutes on this one. It's a long story, but it's important. It's one of the foundations of the science and technology studies field, an early study that was done to look at the politics of artifacts. Artifacts in this case being the bridges. You can see the little overpasses in the picture down on the lower left, the bridges that were built in the 1930s, 40s, and to some extent into the 50s over the Long Island Parkway. The Long Island Parkway was developed to build a road so that people in Manhattan in the mid-century, 19th century, mid-20th century, could find their way out to the lovely new nature reserves along the beach of Long Island. But the person who was building this parkway realized that there were actually already small little roads and paths that the agricultural communities in the area were using. These would cause traffic problems if the carts and eventually tractors were being, crossing this Long Island Parkway all the time. So they decided to build overpasses so that the small roads could run over the parkway, which is a great idea. It's just that the overpasses were built at the time so that they were tall enough for cars to pass under them, but too short for buses to pass under them. And those overpasses still exist now. You can see this is a current map of the New York transport roadwork area, and all of the little pink squares are where there's an overpass that's too small for a truck, that's under 7 feet 10 inches. And so you'll see on the internet pictures over and over again of trucks that run into these overpasses. That's a problem for the trucks. Back in the 30s, 40s, and 50s, this was a problem for anybody who didn't own a car in Manhattan because it meant that they didn't have access to the really lovely rural areas in Long Island. Who doesn't have cars in Manhattan in the 1950s? Well, anybody who's not upper middle class or upper class, which also overlays with race issues in New York and in America in general. So suddenly we had a whole area of the rural suddenly becoming suburban area of the New York metropolitan area that was basically blocked off from people who weren't of a particular class and race area. How does that affect things today? Well, here's the same map only taken from a website where you can check and see what the incomes are of your neighbors. Kind of dodgy, but it's a website that's out there. And the green, of course, is really, really wealthy areas. The red is not wealthy areas. And you can see that in Long Island, this big Long Island out here, most of it's green because guess what? That was the class that was moving out there on weekends and decided that this would be a nice place to build a home and raise a family. And now we have Long Island, which is largely really, really well off suburban area into New York, except for a few little places in some city centers where there have been trains that have been built, and that's where it's more red and white. And this is what I'm saying when I talk about the obduracy of computer programs and AIs that we're building now, that they are going to be taking the values and the intended and unintended discriminations that they're building into them, and these will be with us for a long time. And that's why we have to already now start thinking about what sort of norms and values we're building into our technologies. I'm pretty sure that most of you are already familiar with some of these big cases of existing bias in AI that people have been talking about in the media for a long time. The gender shades work about how facial recognition technologies were initially very, very good at white male faces and very, very bad at Black female faces and sort of scaled in their ability somewhere there in between. Really great work that's actually impacted what's happening now. Or maybe it's the fact that everybody wants to use their phone and there's somebody else with a really commercial big interest to make sure that they can recognize other faces, but that technology is improving. That would be the misrecognition type of biases. There's also things like privilege hazards where we who are not affected by a technology don't realize how bad it is, and we're not in a place, we're feeling motivated to try to change it. And here I'm thinking about the predictive policing algorithms that have been used in the US for at least 5-6 years now. And when they first were initiated, people were talking about how biased they were and how they were predicting crime at a much higher rate for Black people than for white people. And this was a huge uproar, but that hasn't been changed. And those technologies are still being used in the US because the people who might be able to change that don't have really a big reason to do it. That's the privilege hazard of us who aren't impacted by it. Whereas the people who are impacted by it, especially in the US, largely don't even have voting rights anymore and don't have a voice. So trying to figure out how we can get voices and representation from lots of people into these types of technologies so that we don't end up with things like allocation harms, the way that CV bots are like choosing certain sexes and genders over others, and trying to figure out how we can make these even implicit biases in our large language models of visible. It's a lot of work going on there. Where would we start to address this type of fairness? Well, okay, the computer science community has a lot of fairness metrics. In fact, I think I read one paper that like displayed or went through 22 different types of them to figure out how you wanted to be fair, all of them based on mathematics. I think this is fantastic. I'm really glad people are working on that. I'm not sure it's going to be an approach that's going to solve all of these problems, because I think that we also need to be talking about the power dynamics in society that are producing the initial products and algorithms in the first place. But it's also a good place to start talking. So if we're thinking about fairness metrics, I think we have to be able to apply them to things like the data that we collect, sort of pre-processing. How do we think about what data we're going to use? The model generations that we're generation technologies that we're using in the processing, what sort of GANs or diffusion models are we using, and why is that having certain outputs? And then also in post-processing, okay, we get an output from our AI. What are we going to do with that? How should that be embedded into existing practices that are outside of the AI? Is it really relevant? Should we think about how other practices are there and how it can be embedded? All of these are really important places to start thinking about what sort of fairness and power dynamics we need to think about. I'm going to skip this one, but here's like an example of different ways of thinking about fair and unfair in machine learning. I mean, you know, these are really great ways to start the conversation. I'm not quite sure who the audience is. Some of you are maybe really familiar with these fairness algorithms and fairness metrics. We've got to keep working on that. We also have to keep thinking about how they're related to the power dynamics outside of society. And we have to be able to keep using them. I'm just going to briefly talk about this one, but here we've got an example of how in a visual or image-based algorithm has been used to take the original row of the top row of pictures, the top row, and then reduce the quality of those images to make it a smaller file that you can transfer, and then using a special type of software to then try to reproduce the image on the other side once it's been transported. And we see that if we just use the same algorithm for all of the images, row number 3 there, we end up getting faces that look like kind of all the same and yet not, weirdly. Like this is what they're calling white Obama. Because what we need to do is start thinking in terms of fairness and trying to figure out how different types of algorithms need to represent different types of people so that we can actually recognize the diversity that we have. There I use the term diversity, and that's what I'm going to talk about in this next work, which is the work that we're doing. We're looking specifically at synthetic data. Just as a really brief background, most of you probably know it already, but synthetic data, it's actually a term that's been around for years. It's been used by the census community for ages because they think of the data that they actually put out there as being synthetic in order to produce and assure the privacy around it. A lot of that means that it's aggregated data, but the synthetic data term that we're seeing in a lot of areas now is specifically addressing synthetic data that's been produced by machine learning algorithms. This can be like machine learning algorithms that are applied to structured data, tabular data, patient trajectories, financial data, customer data, also multimodal data, but structured data, or it can be unstructured data, which is images and video. People are also calling the text produced by these large language models, for example, synthetic data. I'm going to be specifically in the next slides talking about structured data, tabular data, because that's what we've been working with in order to show some examples that people can understand and innately relate to. But why would you use synthetic data? Because actually it's just fake data. Why would you use that? Well, there's like reasons out there floating around that people think that's going to be great. One of them is that it's allegedly going to ensure privacy. You're going to be able to create a data set that will not be, you will be able to make sure that the people whose data it was based on remain anonymous because it's actually just synthetic data. It's not the real stuff. This means it will also be able to avoid data regulation and provide data agility. And maybe potentially you'll be able to use it to make bespoke data, to work with biases that you recognize and already know exist in your data, and then try to do sampling methods to produce a less biased data. And more frequently, I think people are trying to imagine that they will use synthetic data to amplify data, to take a small data set and make it big enough to be able to then use machine learning algorithms to run on it and find whatever it is you're looking for in your data. Lots of different areas are talking about using this. There's the medical research, the pharmaceutical industry. I guess you guys have AstraZeneca right next door. Lots of stuff going on there, but also financial modeling, forecasting for both things like stock markets, but also climate change. testing and machine learning training and all this stuff, customer analytics, pre-sales samples of data. I mean, just Google this and you'll find loads of people thinking that's going to be a great thing. And you'll find loads of people helping you make your synthetic data. You can either download their tools or they will make it for you. Or you can, find a computer scientist and that person will be able to make it for you, a machine learning expert. Anyways, you can make your own, you can buy it, you can have someone make it for you. Now the big question, what do 44 preschoolers and the country Hungary have in common? They disappeared. So when we started doing this research, given what Sagi and I know about the way that machine learning algorithms work, especially the generative adversarial networks that she's really familiar with, we started thinking that, okay, if we're doing and making synthetic data with tabular data, probably what's going to happen is, if you think of your data on a bell curve, the stuff that's in the middle, where you have lots of really good statistical representation of your data, that's going to be reproduced into your synthetic data. And the stuff on the edges of the bell curve are probably going to disappear. So we used a bunch of different GANs, some of them that had fairness constraints, some of them that didn't, and we started to analyze what was happening into all of these in the new synthetic data. And in one of them, which had like this great fairness constraint, we produced a whole new data set using the 1990 US Census data for the adult population, because that's like an open access large data set that we can use. And in it, we found that the category of adults who had a preschool education, which is a very small category of people, they completely disappeared in our synthetic data. Likewise, in the data set, the original data set, the majority of the people in it, in the middle of the bell curve, were born in the US. But we also had lots of people who had immigrated from other countries out here on the edges. And in the original data set, we had 41 different countries of origin. In the synthetic data set, we had 32. So 9 different countries disappeared and 44 preschoolers. But guess what? We kind of figured that would be the case. That's what the whole way that making these GANs work is. It would make sense. And it's not a brand new observation. In fact, if you go out and listen to lots of podcasts about synthetic data, you will find people talking about their edge cases and pretty much being able to just say, yeah, but you get the really important stuff, and then throwing these edge cases under the bus. Now, I got to say, as a person who works in gender studies, I don't really think that's an appropriate answer. That's a political decision, but I don't think it's really appropriate. So one of the things that Sagi and I have been doing is trying to figure out how we can work with GANs or other ways of generating synthetic data to ensure that we make sure that these edge cases are still represented in the data. And we've been figuring out how to do that to some extent. Now, don't panic. I'm going to talk you through this slide. I'm going to show you one of the examples when we were actually able to make sure that those preschoolers and countries were still in the synthetic data set that we were using. And then talk a little bit about what else we observed happening in it. So in this image, you see the bottom left-hand triangle of the graph is a whole bunch of mappings of 3-point intersections of this same data set, the 1990 US Census data set. On the upper right, in those sort of slightly grayed squares, are the same mappings, but of the synthetic data set. And what Sagi and I are doing with this is we're trying to take a few lessons from intersectionality, which is one of the theories in gender studies that talks about how we are much more than, say, just our sex, or much more than just our class. And all of these different ways of being intersect and create subject positions for us. Now, in the middle of this diagonal on the graph, you will see bar graphs, and that is where we have been able to compare the synthetic and the real data at the single column level. So for example, circled in blue here is the age distribution in the synthetic and the real data. Here it is, a little bit larger. And you can see that the brown is the overlap between them. It's pretty good. It's not identical, but it's pretty good. And you know what, if it was identical, we would have a big problem, because synthetic data has to be a little bit different. Otherwise, it's not synthetic data. Otherwise, it's just your data, and then you don't have privacy. You can't port it. It won't get around GDPR. It's just a mirror of your data. So this, we thought, is pretty good with the age. Now, I turned 50 recently, so I'm actually very glad that we are more than just our age. And Sagi and I started looking at some of the other things in this data, looking, for example, at this intersection, circled in green in the two, of age, income, and gender. Here you can see them up here. Income is binary, high, low on the y-axis. Age goes along the x-axis. And then the gender is the blue and the pink. The left-hand one is the real data. The right-hand one is the synthetic data. And here again, I think we can see that at this intersection, the synthetic data and the real data are fairly close. Not identical, really important. It can't be identical, but fairly close. So this is what we would call a intersectional fidelity in the synthetic data. But then we kept looking, and we saw, for example, down here, and show you these two, the real data on the left, the synthetic data on the right. And if you'll look at this, you'll see that there's an awful lot more pink in the synthetic data. So this little square represents the intersection of occupation, marital status, and gender. Why is there so much more pink in the synthetic data? Well, we went back and looked at the data closely, and we saw that in the real data, there was one data point that was both husband and female, and then had an occupation. This was 1990. We're talking Friends, very cringy period of time in the US. That female husband is most likely a data entry artifact, like a mistake, because I don't think that that was part of the census data collecting process at the time. Could have been, but I doubt it. However, in the synthetic data, we had 200 and I think it was 68 female husbands. So suddenly we had a much larger component of females in the synthetic data, but also we had this thing called, what we're calling now, an intersectional hallucination, which is the existence of something, a type of subject position or data point that doesn't exist in the real data, or exists in one wrong mistake. So basically what we're saying when we're looking at this type of synthetic data analysis is that we need to start talking about intersectional fidelities, where at the intersectional level, do data points actually, recreate the types of intersections that you have in your real data, and intersectional hallucinations, where do they actually just go crazy? This is really innate and easy to understand if we're talking about population data, but it is not only about population data. It would be just as problematic if you say have in your synthetic data 42 oak trees that have 562 pine needles on each tree, right? It's like, it doesn't really matter what sort of data you have, you're going to be getting these intersectional hallucinations and also intersectional fidelities in the synthetic data that you produce. And you know what? You need to have them. Because if you don't have these types of jiggerings, as one of the machine learning experts I talked to use as a very scientific term, if you don't have these jiggerings in the data, then you don't have synthetic data. You just have your real data. But knowing where they are, and here comes Ericka, the social scientist, trying to think about policy is really important. So given that we will have intersectional hallucinations and intersectional fidelities in our synthetic data, we have to realize that these need to be labeled in the data, which means synthetic data is also not going to be a universal solution. Like, I cannot make one synthetic data set and then put it up on an open access repository for everybody to run whatever question they want about on it, because it's going to contain moments of intersectional hallucination that are going to give me a really messed up result. So for example, in this data set, it might be really good to use this synthetic data for questions that are talking about age, income, and gender. But it would be a really bad idea if I wanted to use it for theories or policy decisions that were talking about occupation, marital status, and gender. So we need to be able to make bespoke synthetic data with particular fidelities, or otherwise, for each type of question that we're talking about. This means that I think we need to develop tools that can be complementing the data and attached to the data with explanations and visualizations that talk about where the fidelities are and where the intersectional hallucinations are, because we have to be able to label those, and that has to be able to stay with the data even as it's added into existing real data sets to amplify data sets. Otherwise, we're just going to end up with a big mess of data that has hallucinations in it that we don't know where they are. And that's the sort of question that I think connects very closely to the work that Just Data is doing. So I think I will end there